So E2 mechanisms involved two molecules, and it's an elimination, so that's where that comes from there. So let's have a look at an example, a simple example, the same example as above, where we have CH3, Br, CH3, like that. Okay, and this time what we're going to do, we're going to try and steal one of those CH3s there. So if I just delete that, delete that, change that to 2, put a hydrogen there like that. Okay, so we use exactly the same conditions that we had before, just to show that these kind of mechanisms can compete with each other. We'll use the methoxide ion. This, by the way, would be a sodium methoxide or something like that. So we use the methoxide ion like that, and if I draw the CH3 like that, or minus, for this to be an E2 mechanism, it would depend, if you did the rate, so the rate of the reaction is proportional to whatever's present. In an E1 reaction mechanism, let's call this molecule A, let's change that to blue, see if I can do this, never seems to work for me this. Let's change it to a better colour, a brighter colour, green. Okay, so this is molecule A. So the rate of the reaction, if it's E1, for E1, the rate of reaction is dependent on the concentration of A, and that's it. For E2 reactions, then the rate of the reaction, how fast it's going to go overall, is proportional, that's what that means, proportional to the base and A. Okay? So the rate of E1 elimination is just dependent on the concentration of the alkyl halide, and the E2 rate is obviously now dependent on the concentration of alkyl halide and the base. Okay, so that's very important, and that's one of the reasons we know that there's E2 reaction mechanism, because if we increase the concentration of the base, then the rate will go faster, and if we decrease the concentration of the base, then it will go slower, and so on and so on. So these are the reaction rates which we can get from, if you're not familiar with them, have a look at the kinetics tutorials, and they'll explain what these mean. These are really useful for finding out what mechanism actually happens actually. Okay, so E2 elimination is going to involve two species now. So I'll just get rid of this little bit here. Let's get rid of the reds. Okay, so, and I'll change my pen to red. So if two species are involved, then it must be a concerted process. So this must pick up that, and this bit must go almost immediately, really. So if we draw in the curly arrows, we've got the base coming in, it picks up the proton, the alpha proton. Now this is quite acidic because of this, the reason it wants to leave. So when I say acidic, I mean it will leave quite easily, the proton there. So this is a concerted process now, and concerted just means that it's all happening at once, you know, in concert with itself. So it doesn't take that proton, leave a negative charge there, and then that comes off, because that would then differentiate this from an E2 to an E1, because if you take that off and then that's hanging around, that's going to be the slowest step, isn't it? So this is the slowest step. The slowest step is to get the methoxide and this alkyl bromide species. Obviously it can be a different leaving group if you've got a different leaving group, but this species here and this together as one, and that will give us our product straight away, no intermediates now. CH3 there, CH3. The bromide goes into solution as a salt, and we get methanol as a byproduct. Now that methanol proton is quite acidic, and that will pick it up, and it will be in equilibrium, picking the proton up, because as that one picks that one up, it becomes another methoxide, and so on and so on. Okay, so that's a concerted process. Concerted. And I will write up at the side what that means and why that's important. One thing I didn't mention before, because it wasn't relevant, but it is now, is that these have to be what's called anti-periplanar. Anti-peri, that's an R, planar. Okay, so it's just a little bit extra information, just like I did with the hyperconjugation for you for the E1. And what does that mean? Well, if you remember Newman projections, and if you've not done Newman projections, I urge you to have a quick look at Newman projection, just a way of drawing a molecule. So this bit is the front bit, and actually let's do it in different colours. I don't want to spend too much time on explaining Newman projections, but just for clarity, let's just have a look at this. So a Newman projection basically is a way of looking down your molecule. And why is that going to be important for us? Well, that's going to explain anti-periplanar. So it's a way of looking down this molecule like that. Okay, so we're going to look. Let's have a look down that molecule there, right from that carbon. So that's carbon 1. That's carbon 1, and that one here is carbon 2. All right. Now we're going to draw a Newman projection of that, and that's going to help us to work out how this leaves. Now it's very important, because it can if this can't rotate about this bond, then this bromine won't eliminate and to give this product. So that's why it is actually really important that it goes anti-periplanar. So let's have a look at the Newman projection. Very quick course in Newman projections. The front one we draw like this. Okay. Now you can turn it around if you want, so I could draw it like that if I wanted to. It doesn't really matter. In fact, I will draw it like that simply because I want this hydrogen down. Okay, just because of the way I've drawn it here. So let's just get rid of that. Let's draw that again. Okay, delete that. Right. Get my brush back. So we're going to draw the hydrogen down. That's carbon 1. For carbon 2, if we draw it in a light blue here, we usually draw the next one at the back as a circle. Okay. Now, in order for it to be orientated right, to be anti-periplanar, I'm going to have to draw one up like that, one like that, and one like that. So that's actually carbon 2. I'll draw a little 2 by the side. What I'm going to do, I'm just going to group these together very quickly. Group that. And I'll group this one as well. Group that. Okay, and this one's at the front, so let's put that over the top there. Okay, so that's carbon 1 is the green one, carbon 2 is this one, the blue one. And let's just colour that blue so we can see. Okay, so this refers to this. This is called a Newman projection. I'll just write that down for you. So that's a Newman projection. Newman projection. Okay, Newman projection. Just a way of drawing three-dimensional structure. And it's actually a really good way of drawing this one. So, if I put all the hydrogens in, put one there, one there, one there. Okay, that's the first carbon. Now let's have a look at the second carbon. And that's got a CH3 group attached to it. 2 CH3 groups actually, and a bromine. Now change the colour to blue. So this is bromine. This is going to be a CH3 group. And this is a CH3 group as well. Some people actually write CH3 like this on this side. With the, it doesn't really matter, because a chemist will know that the hydrogen's not attached, but I tend to put them on this side just for these tutorials. But if you ever see me write hydrogens right next to the bond there, it means the same thing. Okay, so what I've done here, I've made it anti-periplanar just for the process of this diagram. This obviously can rotate around this bond here, so it can rotate around. So if I just, well, I'll just leave it actually. If I rotate around this bond, so this goes right in this direction, this goes in this direction, and this goes in this direction. Okay, so the front bit rotates a bit like a propeller, rotates around that bond. Then if you've got big groups on there, then they'll start to get a bit of steric hindrance there and won't want to rotate past, and you get all these different energy barriers and things like that, which I'll cover in a different tutorial. So just get rid of them drawings. But what's important, when the base comes in, so when you've got your methoxide base here, CH3, oh there we are, see I've drawn it like that now. And when that comes in and takes that hydrogen, what we're actually doing is we're creating p orbitals. We're creating a double bond. So remember, a double bond is made out of a sigma bond plus a pi bond. Okay, and a pi bond is between two p orbitals. Now, if you've not done that yet, don't worry. It's really only important if you have covered that topic. All you need to do, the take-home message from this is that this needs to be opposite to that one. So if I draw this structure again in a minute, you'll see what I mean by opposite. This is anti to that. The bromine's not down at the bottom. Okay, the bromine's up at the top there. So if I draw this molecule here, it would look like this. See, there's the H. There's that H there. Okay, it could look like that. And then I'll draw the CH3 there, and the other one's going back, CH3 there, like that. And then you've got one hydrogen coming out there. Hydrogen there, hydrogen there. Okay, so it means it's opposite like that. And it needs to do that in order to eliminate in this anti-fashion. Anti. Now I'm mentioning this because if you remember earlier, I put another type of elimination called Ei. Okay, that's an internal. That's actually because sin. It's called sin when it's not anti. It's sin. So when the bromine's on the bottom there, it's called sin or cis even sometimes. You might have heard this called trans sometimes. So anti is the same as trans. Okay, and sin is the same as cis. Okay. But we call it anti-periplanar, we don't say trans-periplanar. Okay, so it's very, very important that they are, for the E2 mechanism, this is anti-periplanar, otherwise these bonds can't form. Okay, it doesn't form the other way around because the electrons have got to go into the back of this carbon-bromine bond. So in order to go in the back, if it's down there, it'd have to swing up there, and it's a bit impossible mission really. So it goes into this anti-periplanar orientation. So if you can imagine, if you've got a cyclic system, this is where I'm going to with this really. I've spent too much time on this really, but I think it's very important. If you had a cyclic system with a bromide there, and you had a hydrogen there, you can't just eliminate that as you would think, because you have to make sure that these are anti-periplanar or near as anti-periplanar as you can get, so those electrons can line up with a carbon-bromine bond. If they're not, if they're on the same side, so if say the hydrogen's there and the bromine's there like that, then it won't eliminate. So if you've got a methyl group or something else there which doesn't have a hydrogen in the alpha position, then it won't eliminate. It won't go at all. And if that's the case, if it's hard to form this anti-periplanar arrangement, then you'll probably get an SN2 type of reaction instead, so that you'll get a substitution coming in there. Okay, so that's where you get the competition between elimination and substitution. This is this alignment. So what's going to really drive the E2 mechanism? Now the E2 mechanism, as I mentioned, is you've got two species in there in the slowest step, the rate determining step. Okay, just get rid of that. I also mentioned it needs to adopt this anti-periplanar type of orientation. That's really important as well. And I used a Newman projection to explain that. Anti means it's on the other side, really. There is just a few things that could alter the competition, really. So we've got E1, we've got E2, we've got SN1, we've got SN2. Okay, now they're going to be competing. SN2 and E2 are going to be competing, and E1 and SN1 are going to be competing. So what's going to drive that? Well, to be honest, it's quite hard to eliminate a compound like that. So the best thing to do to stop this substituting, so let's just draw the substitution reaction very quickly. CH3 or minus, and you got CH3, just so we can see what the substitution reaction is. Oops, that's a bromine, and that goes to give us our product, which is CH3 O C CH3 CH3 CH3. Okay, and we've kicked out the bromide. So basically, if I just change the colour, let's just change the colour of them so it stands out a little bit. Let's change it to orange, see if that works. No, it's a bit too red. Change it to blue. Okay, so that just comes in, does this SN2 type of reaction, kicks out bromine to give us our product. That's going to be a byproduct of this elimination reaction. So how can we stop that happening? Well, basically, this has got to come in here and attack. So the bulkier this is around the carbon-bromine bond, the better. So steric hindrance is going to help. Now, for that to happen with your molecule you want to eliminate, you're really reliant on the structure, the initial structure. You don't want to be changing that really, because you want to make a product. What you could do, you could change the bulkiness of your base. Okay, so instead of having methoxide, you can have a tertiary butoxide, sometimes written as Tbu or minus, but basically it's that unit there, CH3 C CH3 CH3 or minus, and that will come as a potassium salt or something like that. Okay, so that's a really bulky base, and that's got a lot of electron density around there that's not really a nucleophilic, so it's non-nucleophilic. That's the best way of describing that, non-nucleophilic. Okay, so that will really help. The other things to consider would be low solvent polarity. So if the solvent polarity is quite low, then it's not going to really want to have charged species around, so it's going to eliminate quick. Okay, so it's not going to stabilise. Okay, so just move that around a bit. What's going to happen if you've got a non, well, you need a polar solvent, but if it's not too polar, then this intermediate here is not going to be hanging around for too long, so it'll eliminate, it'll neutralise itself. Okay, so that's important. Strong base obviously will favour the elimination. You've got a weak base, and it's going to be slow, and it's going to be hanging around, so you get nucleophilic competition there. Like I say, high concentrations really help, so that these can actually bump into each other. And high temperatures seem to be favourable for elimination. If you don't have those conditions, then you will find some competition with SN2 and SN1 mechanisms. Now, what I'll do, I'll have to put another tutorial up, because this has gone on quite a long time now, and I'm just going to cover the internal elimination reactions and the conjugate base E1 elimination reactions. And the internal elimination reaction is just basically going in a syn fashion or a cis fashion rather than anti-periplanar, and they're quite interesting. There's a few examples of them around. So I'll discuss them in another tutorial. So bye for now.